Start recording. Hello, everyone. Welcome to the week 4 review for Math 2414. This one we're going to be covering partial fractions and then just general integration techniques. So last week we touched on partial fractions a little bit. If you'll recall, it's just kind of undoing fraction addition. So if we had two fractions, 1 over x minus 1 and 1 over x plus 1, we could add them together by cross multiplying. We get x plus 1 over x minus 1 times x plus 1, and then plus x minus 1. And that would get us to 2x over x plus 1 times x minus 1. And partial fractions, the process is really just kind of undoing this. So instead of starting with this side, we start with this side. And we can write it as the sum of two unknown fractions, a over x plus 1 and b over x minus 1. And of course, we get our denominator simply by factoring. And from here, we know that this should equal this final answer here, which tells us then that the numerator should match. So a times x minus 1 plus b times x plus 1 should get us 2x. And from there, we can plug in different values of x to see what a and b should be. In this case, they would both end up being 1 because that's kind of what we started with. So for example, if we plug in x is equal to positive 1, then we get that 2b is equal to 2. So b is equal to 1, just like we want. And then if we plug in x is equal to negative 1, we have negative 2a is equal to negative 2. So again, a is equal to 1 as well, which matches exactly what we're looking for. But then we do have a few questions about partial fractions, namely, what do we do when we have higher multiplicity denominators or higher power denominators? Because one of the nice things we have in this pretty simple example is that both of our denominators are linear. They have a highest power of just 1. And frankly, it's not always going to be that nice. What if we had a partial fraction decomposition of 1 over x squared plus 1 times x squared? Well, we can't actually just use regular constant a's and b's. In this case, we need to make sure that the numerator of each term has power 1 less than the denominator. So in this case, we're going to break this partial fraction decomposition down into something over x squared plus 1. But we need to make our numerator have a power of 1 less. In that case, 1 less than x squared would be x. So we need ax, and then we need an unknown for each power below that. So in this case, an x to the first and an x to the 0. That gets us an ax plus b. Similarly, we have over x squared here, which means we would need a cx plus d like that. Now, some of you guys probably see it broken down a little more frequently as c over x plus d over x squared. Is that right? Yeah. This is another way that works exactly fine. In fact, they're pretty much identical. You can see that if you multiply this by x over x. This is cx over x squared, and then we could combine it with d over x squared to get cx plus d over x squared. The reason you'll see it done this way sometimes is because it sometimes makes your step up here a little easier, where you might have to, it just makes it a little easier in simplifying later on. This way, I like showing people this way because it's a little more consistent. It's just every time, you don't have to think about, well, have I already included this power on a lower term? So you'll notice we just have a d over x squared. That kind of breaks our rule that the numerator should have 1 term for every lower power. So in this way, it's just a little more consistent. You just think, I have 1 term for every lower power, and that's all I need to consider. Of course, you could just go through and immediately simplify it into this, but that's just kind of a general rule of thumb. Either way works, of course, it's up to you. Any questions as to how we broke that down? All right. So let's go ahead and finish off this partial fraction decomposition. Actually, do I really want to do that for this one? No, we'll go ahead and do it. So we have ax plus b times whatever's missing, which is x squared, plus now we have cx plus d times whatever is missing, in this case x squared plus 1, and all that should be equal to the numerator on the far side, 1. Now I have a few tricks up my sleeve. First off, I can plug in any value of x, and this equation should be true for any value of x. I can also, actually, yeah, we'll just start with that. If I plug in x is equal to 0, well, all of this immediately vanishes because I have 0 times a plus b, which is 0. And then my c term is also going to vanish, so I'm left with, stop jumping all over. I'm left with d times 0 plus 1, so d is equal to 1. Pretty straightforward. Now, I also can match up different powers of x. So in this case, I'm going to look at just the x cubed terms. I have ax times x squared gets me ax cubed. And I also have cx times x squared gets me x cubed. And on the far side, I have no x cubed. So what this tells me is a plus c should equal 0. Now I can also do the same thing with x squared terms. bx squared plus dx squared should also equal 0. So b plus d should equal 0. But I already know d. It's 1. So then b is equal to negative 1. Now, I really can keep going like this. I'm just going to do x terms now. In this case, everything on this part has an x squared attached at least, so I can just ignore that for my x terms. Here, I can have cx times 1, so cx is equal to 0 on my far side, so c is equal to 0, and of course, since a plus c is equal to 0, that tells me that a is equal to 0 as well. So my total partial fraction decomposition would be negative 1 over x squared plus 1 plus 1 over x plus 1. Right, that's my d value, yes. B, and then a and c. And it just so happens that I didn't happen to have any x terms in my numerator. That should not be an x plus 1, sorry, that should be an x squared.
How did you do the c thing? Because shouldn't it be c plus b x squared equals 0?
Ah, so you're wondering how I did this portion?
Yeah.
So this one, I'm just looking at x terms.
Oh,
so
okay.
I can immediately ignore any of these because they all have at least an x squared attached. Then d will only have an x squared and a constant, and c is going to have an x cubed and a single x. So I'm just looking at the cx is equal to 0x on the other side.
Makes sense.
All right, any other questions? All right, cool. In that case, practice. Write the general form of partial fraction decomposition for 1 over x squared plus 4 times 7x times 2 minus x times 3x squared plus 2. And don't solve for your individual constants, just write out the general form.
Is that a 2 minus x or 7 minus x?
That's a 2 minus x.
I'm too brain dead for this today.
Have you done it?
Yeah.
All right, perfect. Read out your answer.
Wait, ax plus b over x squared plus 4 plus c over 7x plus b over 2 minus x plus dx plus f over 3x squared plus 2.
All righty. Perfect. Exactly right. Basically pretty straightforward. We've got a power of 2 on the bottom, which means we're going to need an x term and a linear term on top. Here this is just linear, so we need just a constant. Again, linear, just a constant. And again, a power of 2, so we're going to need a linear and a constant term. Fairly straightforward. Nice work. Go ahead, box around it. What?
I said thank you, good sir.
Of course. All right, now time for some more practice, some actual enemies. Here we go. Good luck. I'll give you some time to work through those. All right, let's go over this first problem. So first off, we're going to want to factor our numerator. So 3 over x cubed minus x squared is of course equal to 3 over x squared times x minus 1, which tells us then that our partial fraction decomposition should be ax plus b over x squared plus c over x minus 1, or equivalently, a over x plus b over x squared plus c over x minus 1. Now we can go ahead and work through our partial fraction decomposition. We know that a needs to be multiplied by x times x minus 1, b needs to be multiplied by x minus 1, and c needs to be multiplied by x squared, and all of this should equal 3. So if x is equal to 0, then we have negative b is equal to 3, so b is equal to negative 1. If x is equal to 1, then c is equal to 3, and we're just done. And finally, I'm just going to count my x squared terms for the last terms, the last ones, and that tells me that ax squared plus cx squared should equal to 0x squared, so a plus c should equal 0, so a is negative 3.
Shouldn't it be negative 3?
I was
You
just about
wrote
to
it
say.
wrong.
Oh, well, yes, you are right. B should be negative 3. Perfect.
Did you read your b as a 3?
I don't think so. I think I just messed up. All right, so then we have the integral of negative 3 over x plus the integral of negative 3 over x squared plus the integral of 3 over x minus 1. And of course, I need to attach my dx to each of these. And these are all fairly simple and straightforward integrals. We have negative 3 natural log of x plus 3 divided by x. This is just using the power rule. And then plus 3 times the natural log of x minus 1. And of course, we have our plus c up front. All right. Here we go. And that's what you guys both got, right? Perfect. All right, we ready to go over problem 2?
Oh, wait, what was the answer?
Oh, I think you got it right. Yeah,
Yes.
good stuff. All right. Perfect. Question 2. This time, again, we're going to start by writing out our partial fraction decomposition. We know that 2x plus 3 over, I conveniently gave it to you in factored form, should be equal to ax plus b over x squared plus 2 plus c over x minus 2. Okay, now that tells us that ax plus b times x minus 2 plus c times x squared plus 2 should equal to 2x plus 3. Now, if we let x equal to 0, actually, I'm going to start with letting x equal to 2. If we let x equal to 2, then all of this disappears. We're left with 6c is equal to 7, so c is equal to 7 over 6. Yep. Okay. Oh, I messed that up in my notes. Okay. Now, if we look at just the x squared terms, I have an x squared term from a times x, and I have a cx squared term, and that gets me no x squared terms on the other side. So a plus c is equal to 0. So a is equal to negative c. So a is equal to negative 7 over 6. And finally, I'm going to look at just x terms. I have negative 2 times a times x plus b times x should equal to 2x. I don't have any x terms for my c value, so that tells me that negative 2a plus b should equal to 2. Or in other words, negative 2 times negative 7 over 6 plus b is equal to 2. So 7/3 plus b is equal to 2. So b is equal to -1/3. Right?
I got 11/6, so I don't know.
You got 11/6, huh? You might have flipped a sign somewhere, if I had to guess. But yeah, I think I messed this one up originally in my notes because I did 2 squared and got 2, which is not right at all. But we're going to work through from this. We have, now we can plug our A's, B's, and C's in. And we have, here we go, the integral of -7/6x plus, or I guess -1/3, all over x squared plus 2, plus the integral, or plus 7/6 times the integral of 1 over x minus 2. Right? Now, do you know how we would integrate this portion right here?
Another partial fraction.
No, because our denominator is just one term, right? So we don't want to do partial fractions again.
Is it u sub?
Yeah, we could do u sub after a certain point, though. What I'm actually going to do is I'm going to split this up into 2 integrals. So this is -7/6 times the integral of x over x squared plus 2. In fact, I'm actually going to make this 2x and then a 12 on this bottom. And then I have -1/3 times the integral of 1 over x squared plus 2. And I still have plus 7/6 integral of 1 over x minus 2. Now, the reason I put this 2x here is because now this really well matches for a u sub if I let u equal to x squared plus 2, and du is equal to 2x. And this would get me 1 over u du.
Sorry, where did the 12 come from?
So when I got this 2 on top, I needed to multiply by 2 on bottom so that I wasn't just multiplying it by 2. Sorry, that could be a little confusing. All I did is I multiplied by 2 on top and bottom. But now it perfectly matches u sub. This becomes the integral of du over u, which is, of course, just the natural log of u. And, of course, I know what u is, so that's -7/12, natural log of x squared plus 2. And because x squared plus 2 is always positive, I can just drop my absolute value bars as well. All right, next up, I have this one. Do you recognize that fun shape? What should that go to?
Isn't that the arctangent?
Right, that's an arctangent integral. So that's going to become -1 over 3 square root 2 arctangent of x over the square root 2. Because in this case, our a value is, or a squared is 2, so a is root 2. Our integral in general of 1 over x squared plus a squared is equal to 1 over a arctangent of x over 3. That's the general rule we're using there. And finally, this one's just a basic natural log. And we have our plus. So there is our final answer. Any fun questions? Yeah.
So how did you know to split up that first integral into 2? Like, what was the giveaway?
The giveaway was really, you said your first thing you said was u substitution.
Yeah.
And I was like, yeah, u substitution is a good idea, except I'm only going to be able to substitute out for the x, right? So I know like if I split it up, then I could do u substitution on that part. And then I looked at it and saw, oh, that'll leave me with something that looks a lot like my arctangent formula. So u substitution is a really good thing to try first, because it can help you simplify and recognize some patterns. So that's just kind of my thought process. I thought I'm going to need to substitute out just the x. To do that, I'm going to need to break it apart into 2 integrals. Good question. All right, you ready to move on? Okay. All right. Now, last thing we're going to talk about as far as partial fractions go is what if the numerator has a higher multiplicity than the denominator, or a higher degree? Well, in this case, we basically always want to do polynomial long division. Because a lot of our integral techniques work for functions that are bottom heavy. So let's say we just had an example. We had x squared minus 3x plus 2 over x plus 4. Well, our biggest term on top is an x squared, our biggest term on the bottom is x, so the numerator has a higher degree than the denominator. Now, what we want to do is we want to do polynomial long division because this is going to get things in forms that are a little more familiar to us. So, for polynomial long division, if you'll recall, we start out by looking at this biggest term here and say x times what gets us x squared? Well, x times x gets us x squared. So then x times x is x squared. Then x times 4 is 4x. And that is what we need to take away. X squared minus x squared is 0. Negative 3x minus 4x is negative 7x. So now I think, well, x times what gets negative 7x? Well, that would be negative 7. So then negative 7 times x is negative 7x. Negative 7 times 4 is negative 28. And of course, I subtract this. So negative 7x minus negative 7x is negative 7x plus 7x is 0. Then I have 2 minus negative 28 is plus 30. And that would be my remainder. 30, of course, I still need to divide that by my x plus 4. And this would be the result of my polynomial long division. Not the final answer yet. We still need to integrate. But the nice thing about what we've done now is we have a nice polynomial plus 30 over x plus 4. And 30 over x plus 4 is in a nice form for just using a natural log. And I can basically just integrate this using all the fairly simple rules you've learned so far. The integral of x is 1/2 x squared. The integral is 7x. And this would be 30 times the natural log of x plus 4. And of course, I have my plus c at the end. Any questions?
Isn't x plus 4 different?
You got it? All right. On this side here. I'll give you guys a quick practice problem. Good luck.
We factored the numerator. Is there a way to do it that way that's easier?
Well, in this case, no, because none of the factors of the numerator correspond with the factors of the denominator, so nothing's going to cancel nicely. In other words, you're going to have a remainder, so there's not really a way around it.
I just know if there's a way for to factor out and then do polynomial division easier.
In general, no. Polynomial division likes our polynomials in non-factored form, because then it's really easy to see all the coefficients.
You can nod my head like I understand.
Basically, once we start factoring, it's really hard to see what these coefficients here are, or I guess you can't see that. It's really hard to say, oh, we've got a -3 here, or oh, a 2 there, because it's just factoring kind of hides that. Factoring gives you other useful information. do not see one. Nope. There might be one in.
Did they ever fix the link, by the way?
Okay. I don't ask questions. All right. Are y'all ready? Perfect, perfect. So again, we're going to be wanting to do polynomial long division because x cubed is a higher power than x. Ah, stop that. Okay. So we have on the inside x cubed. And I'm actually going to include 0x squared and 0, just to remind me to have some spacing. Now I think x times what gets me x cubed? It's of course x squared. So that gives me x squared times x is x cubed. X squared times 2 is 2x squared. And now I can subtract these. X cubed minus x cubed is 0. 0x squared minus 2x squared is minus 2x squared. And that's kind of why I put in the spacing, just so now I have room to include those x squared terms. Because now I need to think, well, x times what is negative 2x squared? That's, of course, negative 2x. So negative 2x times x is negative 2x squared. Negative 2x times 2 is negative 4x. And then I subtract that. That gives me 0. Negative x plus 4x is 3x. So x times what gives me 3x? It's, of course, 3. 3 times x is 3x. 3 times 2 is 6. And I subtract this, and that gets me minus 6 as the remainder. So now my integration becomes the integral of x squared minus 2x plus 3 minus 6 over x plus 2. And this integral, again, just power rule and a natural log. 1/3 x cubed minus x squared plus 3x minus 6 natural log of x plus 2 plus c. Any questions? All right. Cool. Well, let's really quick do a recap of the integration techniques you've learned so far. Of which partial fractions is just one. So outside of just applying your basic rules and your basic like natural log, arctangent, stuff like that, when you have a more complicated integral, what have you learned to do? So first off, you want to try and simplify the integrand. Cancel things if you can. Do long division like we just did, things like that. So what can you cancel? What can you divide? Basically, how can you make the problem look nicer? Well, from there, you usually want to try and make a nice substitution. So for example, U substitution. I like to try U substitution. U substitution is usually one of the first few things that I try when I'm integrating. If U substitution doesn't quite work though, or if you can't find a good one, try and look for some nice patterns. So for example, trig sub usually has very distinctive patterns. They're usually like 1 minus x squared and a square root, things like that. So those usually have pretty distinctive patterns. Similarly, if you notice the product of two things you know how to integrate, that's a pattern that could tell you maybe want to do integration by parts. Or basically all of your partial fractions problems thus far have been with dividing two polynomials or some kind of rational functions, giving you partial fractions. So a lot of the integration techniques you've used so far often have specific patterns associated with them. So see if you can find those patterns. And lastly, if none of those things work, try again. Get clever. You might have to manipulate the integrand. So do weird things like adding in a certain term and then taking it away so that you can split your integral into two things you know. You might need to apply some log rules or some exponential rules in order to make it look a little prettier. Just things like that.
Wait, is there still an integration technique we haven't learned?
There are so many integration techniques.
I was told there were 5 main ones, and I only count 4 up there.
These are just it's just kind of a general strategy for solving integrals.
No, I was talking about like your bullet points. I was talking about there's U sub, trig sub, integration by parts, and then partial fractions. That's only 4 or 5.
There's probably another. I might be lumping things in together. See, I basically learned that there are practically 2.
Yeah,
U sub and integration by parts.
Yeah.
Because really, doing trig sub is just kind of another form of substitution. So it's really just substitution and integration by parts. And then partial fractions, you're just rewriting your problem. That's all it is. So giving it a new name is fine. You can do it if you want, but yep, it's just, there's a lot of integration techniques. Some of the main ones are just substitution and integration by parts though.
This is a side note, but are there any things that we cannot, like, have no way to integrate?
Oh, certainly.
Oh, there's a lot of.
Well, there are problems. There are things that when we integrate, they don't give us what's called an elementary function. So you have to kind of invent something. So like if we tried to integrate the function e to the x squared, we can't represent this using polynomials, using exponentials, using logarithms. We can't represent this integral using anything like that. We had to come up with a whole new function specifically to represent this integral. So it's not really elementary. And you can't really integrate it using any of the known techniques you have because it comes out to just a whole new function. But that's a good question. So yeah, there are things you can't integrate.
We don't have to worry about those though.
Right. All right. Let's go ahead and do an example. Let's see if we can integrate secant cubed. So first off, if I tried to do u substitution and let u equal to, secant of x, because that's really all I can, well, then my derivative is secant x times tangent x, but I don't have a tangent in here. So I don't really want to do that. If I tried trig sub, well, it doesn't have my nice form of something of like 1 plus x squared or something like that, so it's probably not trig sub either. It's obviously not partial fractions either. So really my other main thing that I have left is integration by parts.
Couldn't you also do the, you take out since it's an odd power, you take out a secant, and you take secant squared and turn it into 1 minus tangent squared.
Right, but in this case, again, my u substitution needs just one tangent, and it's really hard to do power reduction from like a tangent squared down to tangent, right?
Well, if you have one tangent left, then what you're going to do is you're going to turn that into.
Right, but we have 2, right? So you have a good idea. You're saying take it secant of x, and then secant squared is going to tangent squared plus 1, right?
Yeah.
Well, I know how to integrate just secant, so the secant x times 1 is fine. But do I know how to integrate secant of x times tangent squared of x? Because if I try u substitution, if I let u be secant x, then then du would be secant x tangent x, and I have an extra tangent and not enough secants. If I let u be tangent x, then du is secant squared, I have an extra tangent and not enough secants, right? So here we've run into a problem, right? That's our problem with our fun trig integral, right? So maybe let's try a different technique.
I'm just thinking about all the ways you can do it, but yes.
Yeah, so that's kind of what integration is about. You try it one way, if it doesn't work, try something else.
Well, I meant like, because you could also replace tangent again, or you could turn tangent into sine over cosine. But it's going to be more complicated.
Yeah, it's going to get convoluted and stuff, so we're going to go with integration by parts. And it definitely helps because I worked this one out in advance. So, and also this is a problem that really doesn't look like it should be integration by parts, but you'll probably see it later. So, I'm throwing it at you now.
Thank you. Thank you.
By parts. Well, first off, my one thing that I need to do is I need to make sure that I can integrate my dv, right? So when I'm choosing my dv, I need to make sure I can integrate it. And I think I might as well make it a nice, pretty integral. I know that the integral of secant squared is exactly equal to tangent, right? Which means that my u should just be secant.
Rho dx.
And then my du would then be secant x tangent x dx. Which means that this integral is now u times v minus the integral of v du. So this is secant of x tangent squared of x. And you'll coincidentally know that this is actually the same problem we ran into here, right? But we're already doing integration by parts, so we might as well do it again, right?
Okay.
So this time, actually, we're not going to do integration by parts again. What we're going to do is we're going to take this, and now we're going to apply one of our trig rules again.
1 minus secant squared. So I was thinking that they go over to the left.
Yeah. So there are multiple ways we can solve an integral. We might actually go back and see if we can solve it from there. Minus, here we have the integral of secant of x, and then tangent squared is 1 minus, or secant squared minus 1, right? Yeah, secant
Yes.
squared minus 1.
Did I say 1 minus?
I don't know.
Okay.
All right. Well, now I'm going to distribute.
So should you always distribute?
In general, it helps to distribute when you're integrating, unless you're specifically trying to make a u substitution and separating your u and your d. So here we have minus secant times secant squared is secant cubed. And then I'm actually going to go ahead and distribute this. So we have secant times -1 is negative secant times -1 gives us positive the integral of secant of x. Right?
Seems like a loop.
You're right, it does. So I'm just going to take this and copy it and put it right down there. Perfect. And now we're just going to add that same integral to each side, right? Right? So this cancels with this. 2 integral of secant cubed of x is equal to secant of x tangent of x. The integral of secant x is something you should have memorized, the natural log of secant x plus tangent x plus c. And then we can just divide both sides by 2 to get our final answer, right? So then we have on this side, the integral of secant cubed of x is equal to 1/2 secant x tangent x plus 1/2 natural log of the absolute value of secant x plus tangent x plus our constant. Yep.
So I've seen the professor do this before in class, and you end up with the same integral and you add it back. Does that usually happen in cases when you have just like one trig function by itself, and you can't just cancel easily?
Sometimes it does happen a lot with trig. It happens a lot with e to the x as well, because those are the things where you'll start seeing their derivatives show up again, because their derivatives are often cyclic. So if we take the derivative like sine, we'll get cosine, but then if we take it again, we'll get back to sine, and that fits in with the original as well. So it's just things that you'll see when your derivative gets back to where you were.
Will we ever have to solve for C in integral calculus?
Solve for C? Maybe. Depends on if your professor wants you to.
I hope not.
Are you ready for some practice problems? All right. Yeah. Okay. Fun stuff. All right, go ahead and give those two a try. How's it going?
My first idea did not work out.
Oh. It's okay, on this one mine didn't either.
Huh?
On this one mine didn't either, so. Just fun things.
I just don't know how to do the other way.
Well, try rewriting it, making it look different.
That makes no sense to me.
How are you doing?
I had to do something going on, but it didn't work out, so I restalled.
Good. you happen to remember any fun rules you can use with exponents?
There's not one thing that's multiplied by everything.
Right, but if we are adding two things as an exponent, we can actually rewrite it somewhat differently, right? If it's two exponents being added, we can rewrite it as the product. Does that help us? Yeah.
Now you can technically have XE.
So what are we going to do from here?
Integration of parts.
We could do it. Well,
Use of
I would lean more towards USA. What's the substitution we're going to make?
E to the X.
All right, we'll let U equal e to the x. What now?
Du is E to the X. Oh,
So then this becomes e to the x dx turns into our du. We have e to the u du. What's the integral of that?
E to the U.
And then we substitute our u back out. Fun stuff,
I'm
right?
just not here for it today.
Okay, that's okay. All right. Now, second one.
What if you have a checkerboard and then two quarters are missing, but they're on the same?
What?
It's two supposed to be
Is 2 supposed to be what?
true.
No, you shouldn't have to do that. What are you thinking on that one?
Is this where you multiply the conjugate?
Oh,
Um,
yeah. That might
I wouldn't really do that because then you're just kind of throwing in new things. Are there any substitutions you can make? Any way you can simplify it with a fun substitution?
I got that.
Alrighty. Well, we could start by factoring it, right? Or factoring the denominator.
Oh, yeah.
Right? Well, one thing I know from taking the derivative of the square root of x so many times is if I take the derivative of the square root of x, then I end up with the square root in my denominator, right? So I'm going to try and see if I can use that fact to tell me where my du should end up. So I'm going to let u equal to the square root of x. And then du is equal to 1 over 2 times the square root of x, right? Or in other words, I can just multiply both sides of this by 2. And I get that 2 times du is 1 over the square root of x.
Why not just cancel it?
Why not just cancel it?
Yeah. Why not like move your square root of x 2 over 1 plus x squared, or 1 plus x.
So can you clarify?
So multiply by the square root of x, so that'll cancel. And then on the other side, you have to do the same thing. So you're left with 2 square root of x du. And that square root of x will cancel in the denominator of your actual integral.
So what would the end result be?
The 2 over 1 plus x.
Well, no, because that would change things, I think. Are you saying just multiply by the square root of x? Because if we multiply the top and bottom by the square root of x, we have that there, right? But then the square root of x times the square root of x would give us an x on the bottom as well.
My math and your math are very different.
Yeah, I'm thinking we might be misunderstanding each other.
So like for your du, if you multiply the denominator on the right side, the square root of x,
Mhm.
if you multiply by that on the other side, you get 2 square root of x du, right?
Right.
And so then you plug in, so now dx is equal to du2 square root of u du, or square root of x du.
So you're just talking about doing a different way of substituting.
Yeah, and then now your square root of x will cancel,
Right.
and you're left with 2 over 1 plus x, which is a nice ln, 2ln.
Right. Another way you could do it is just look at where your patterns are. So I notice I have a 1 over x dx, so I'm going to immediately turn that into my 2d. Same result, but then we still have a 1 plus x on the bottom, right? And the problem is this isn't a natural log. Because this is a du, we have an x there. In order to do our integral, everything needs to be in terms of u. Luckily, we know that u is the square root of x, so u squared is equal to x, right? Is that a familiar integral?
Yes.
What's that?
Arctangent.
Right. And we can just substitute u back out. And we get 2 times the arctangent of the square root of x.
Oh, I see what you did with the 1 over x, because that's how you got rid of it. Okay.
Yeah, all I was doing is I was just kind of looking for where my patterns were. So I said, here's dx over x. This is dx over x.
Makes sense.
Fun stuff. So again, the big clue here was if I made the substitution u is equal to the square root of x, that's a really easy way to get the square root of x out of my denominator for my substitution. That one's a little hard to see. I'll say that. It took me a minute when I was doing it, so don't feel bad if you didn't see it at first. Yeah. Would you like to do one more practice problem, or go for it? One more? All right. This one we might have to speed through a bit.
Yeah.
All right. E to the 2x divided by 1 plus x.
I don't want all your internet searching to be for nothing.
Textbook.
Textbook searching.
Yeah. What are your thoughts?
I feel like it's some rule that I don't remember. Like some way they all relate to each other.
Not really.
It's e to the x squared, and then like you separate your x's out, 'cause that's what my mind was trying to do. Oh yeah,
Right, that's true. Well, we also know that, what if we let u equal to 1 plus e dx? What happens then?
you get e to the x, and the integral of e to the x is e to the x.
What's our du? Right?
Yeah, but that cancels something, doesn't it?
Well, it cancels some stuff, right? So the du, or the u, is on the denominator. One of my e to the x's becomes my du, right? But I still have an extra e to the x on top. How can I get rid of that?
2u.
No, that would be more like du squared, and I don't have enough dx's for that, right?
No.
Yeah, so we only want to substitute out for du once. What about this? Can I use this at all?
U to the x equals u minus 1.
So I'm going to take that extra e dx and put it in right there. Now, how can I integrate u minus 1 over u?
E minus, wait,
Can you split that up?
Split it up, right? So what does it become?
1 minus, or
Right, 1 minus 1 over u. And of course, the integral of 1 is just u. The integral of 1 of u is the natural log of u. And then I just take u back out. And to be really fancy, I can just put my plus 1 into my c. And that is my final answer. Any questions? All right, perfect, perfect. In that case, thank you very much for coming, and have a nice